Welcome everybody to another rootlabs at lunch, picking up after the holiday break. It's a platform where we intend to share knowledge about data and AI. So plan is to organize 2 sessions per month. So as we speak, we're working on a schedule. So more sessions will be posted on our meetup page. So should you have any questions during the presentation, you can use the chat and we'll visit these after the presentation of Murillo. So today we have Murillo is going to speak about neural recommender systems and neural collaborative filtering in particular. So Murillo is a machine learning engineer at DataRoots. He's Brazilian. He also business science degree in mechanical engineering and also a Master of Science in Artificial Intelligence here from the University of Leuven. He's a Google Cloud certified data engineer. And yes, you're also the co-captain of the DataFoods team. So yeah, we're ready for your presentation, Murillo. Go ahead.
All right. Okay, can everybody hear me fine?
Yes, we can.
Okay, that's good. Okay, so yeah, now that we've gotten acquainted, this is just a quick agenda of what I have planned for today. So the final destination, let's say, as you mentioned, Bart, is the neural collaborative filtering, which is, by the way, from this paper, really good paper. But before we can talk about neural collaborative filtering, we're going to talk about recommender systems in general, the wheres, the whys, and hows. And then we're going to focus more on collaborative filtering. So we're going to dive into math here. And then we're going to talk about the addition from this paper, the neural collaborative filtering. We're going to have a quick demo and then some time for question and answers. Okay. So recommender systems. We probably all interact with recommender systems every day. Well, Netflix, Amazon, Spotify, Google, those are the big ones. But more and more, they're becoming more important. And why? Because nowadays we have a lot of options. We have a lot of choices, and usually that's perceived as a good thing. But sometimes when we have too many options, we may have a hard time actually selecting what's the best option for us. Actually, Semantic Scholar in 2018, they conducted a study that they found that over 3 million papers were published. That's over 8,000 papers a day. So for people, any PhD students out there, you know that it's impossible to read 8,000 papers, or even like, I think it's unlikely that you'll be able to thoroughly read one paper a day. So how do you select the papers that you want, or how do you select the items that you want? What's the best fit for you? And how? Well, there are 2 main approaches for recommender systems, the content-based and the collaborative filtering. The content-based, the idea is that I'll predict what you like based on purchases you've made in the past or information about yourself, right? So it could be gender, nationality, age, and whatnot. And in collaborative filtering, on the other hand, the idea is I'm going to try to predict what you like based on what similar users have purchased in the past. So in this example here, the party guy and the devil, they're considered similar because they both purchased the confetti and the beers. But in this case, the devil also purchased the slot machine, so that gets recommended to the party guy. And as I mentioned earlier, we're going to be focusing on collaborative filtering from now on. And with collaborative filtering, there are a couple of hardships when you try to implement them. So this is kind of going a little bit aside from the theory. One of them is that the feedback that we get most of the times, well, there are 2 types of feedback. There's explicit feedback and implicit feedback. Explicit feedback would be if you watch a movie, for example, and you tell me if you liked it or not, or how much you liked it. And implicit feedback would be, I only know that you watched the movie. And in real life situations, in business case, usually you have implicit feedback, which poses a hardship there because maybe you didn't like the movie. Like the movie you didn't watch is not because you didn't like it, it's because you were unaware of it. So it's a bit harder to evaluate the recommender system in that sense. And also, the other hardship on evaluation is that a good recommender system should recommend you something that you wouldn't find by yourself, right? So if I have a recommender system that just recommends the most popular items all the time, that's not a really good recommender system. And the other issue is the code star problem. So in collaborative filtering, like I said, I find out similar users to you based on purchases you've made in the past and what other users purchased in the past. If you just signed up to a platform, I don't have any purchase history. So I don't know what you like and what you don't like, and I can't compare you to other users. And when you don't have information, past information, then usually people fall back to a content-based. And in reality, most of the times you have a hybrid between these two approaches right here. Okay. So now we're going to focus more on the collaborative filtering. So we're going to dive a bit deeper in the math. So brace yourselves on this part here. The key idea with collaborative filtering is we try to come up with these embeddings, these vectors here, these latent vectors. In this example, we have movies, and then we have users here, right? So the items in this case are movies. And we try to come up with these vectors for these movies that capture some meaning, right? Is this a comedy, terror? Is this for children? Is this animation? And then same thing for the users, right? This vector should represent in some level, do you like comedy? Do you like terror? Do you like children's movies, or etc. And once we have these two, we try to use these two vectors to make a prediction whether you're going to like this and how much you're going to like this, right? And then the idea is for each user, we're going to give the most likely ones that you're going to like that you haven't seen already. This image, by the way, is from Google developers, and we'll put all the links on the YouTube description, but I'll have to check on bottom that one. Okay, so how do we do this? How do we come up with these embeddings here, right? And that's with matrix factorization. So forget about the matrix for a second, but when we have in multiplication, right, if you have A and B, we can multiply A and B to get C if they are numbers, but we can also factorize C to get A and B. And we can do the same thing with matrices, right? We have a matrix A multiplied by matrix B, that we get matrix C, but we can factorize matrix C to get matrix A and B. And we're gonna try to do the exact like this, going from right to left. So applied to our problem. If you imagine that each check mark here is a positive one, and each blank space here is a negative one, then you have this interaction matrix. And this is the matrix that we're going to try to approximate. And the way we're going to actually do this matrix factorization, we're going to factorize this, is with machine learning, right? So after we train the model, everything, we should get something similar to this, right? What we're training is this matrix and this matrix, which you could have guessed by now that these are going to be the embeddings for each of the movies and the embeddings for each of the users. And this, you can see that this matrix here that we're approximating is just going to be the product between these two matrices here, right? So if you take this -1 here, it's 1 times -1 plus 0.9 times 0. And this is going to be true for all the elements in this array. And again, it's not an exact match of this, right? But it's an approximation. So this should be close to 1, which is 0.88. This should be close to -1, which is actually exactly -1. And this is what we have after training. Before training, we're going to have this matrix is going to be random, right? And this is going to be random. And then consequently, this product is going to be random as well. And then what we try to do is compare each element of these ones. And then we have a mathematical expression to compute the error, right? And then we can use gradient descent, singular value decomposition. If you have explicit feedback, you can use the weighted alternating least squares and whatnot. So there's a lot of optimization options here as well, but we can stick to gradient descent because the next thing we're going to talk about is neurocollaborative filtering. So in this paper, the main addition that they have to this is for each user and each item. So we're still going to have the vectors for each one, but we can concatenate them and actually pass through a neural network. And in this neural network, we can have nonlinear activation functions, which is something that you don't get by computing the product between this vector and this vector, right? So you get more interesting features from here. And in the end, you still have a score and a target, and you still compute with a sigmoid, right? To get some, or a hyperbolic tangent or something within your boundaries. This image, by the way, is also from the neurocollaborative filtering paper, which we'll try to put the link in the description of the YouTube video. So in the paper, they don't propose just replacing the matrix factorization, but they propose putting it side by side, right? And then now we also have two different embeddings, one for the matrix factorization bit, so this general matrix factorization layer, and then another embedding for the MLP, so the multi-layer perceptron, right? And yeah, you pass everything through here, and then you pass it to a sigmoid, and then you can actually compute the loss. And the paper also suggests doing this separately. So train the matrix factorization, and then train the multi-layer perceptron, and then use transfer learning to fine-tune all this whole process here, right? And this is pretty much it. So I'm gonna go now to the demo that I prepared for you guys. And just to start off, this is the tensor board, right? So this is showing the graph, which again is very similar to this, right? We have this would be the matrix factorization bit, and this would be the neural network bit. And then we concatenate those and pass it through an interaction. So this is what this is what we've built on TensorFlow, and I'm gonna show you the code, which also is gonna be available on a Google Colab or the binder or something, okay? So first thing is we have the imports here. We used TensorFlow, LightFM, Pandas, and NumPy, right? These are the versions. This top K here is the number of recommendations we're gonna make, right? So in this case, let's say if the top K was equal to 2 for this example, and we had this user here, we would pick the highest 2 values for the movies, right? So it would be the 0.11 and the point, I guess would be the first 0.09. And the number of epochs is just for training, right? So again, this is just the image to remind us what we're looking for. The data set that I used is from the LightFM. Actually, LightFM is a popular hybrid recommender system. So you can use it off the box, and we're gonna compare that in the end. I fetched the data set from there, and this is just to visualize. I just took the first 10 movies and the first 10 users. And this is actually an explicit feedback, right? So people actually gave ratings between 1 and 5. So this is what we would have. And what I did here is just say, okay, I don't want anything that is below 3, right? Because anything below 3 is something that people didn't like, so I'm not interested in that. I also wanted to mimic something that is closer to implicit feedback. So I made the values here binary, 1 and 0, right? And again, this neural network, it also expects one user and one item each time. So I went from this wide format to a long format. So now I have the user ID, item ID, and interaction being if it liked or it didn't like, okay? Here's where we're building the neural network model. And again, this is just a reminder, but it's very close to this one that we have on the tensor board. And yeah, so here we have the input, which is just a number to represent which user we're talking about. And then this is the matrix factorization embedding. And these are the MLP embeddings, right? So like I said, they're different. They can have different sizes as well, which they do in this case. They're all specified here. For the matrix factorization, we just flatten them, and then we just do a multiplication. So it's really just a matrix, matrix product, like a dot product between these flattened vectors. And for the MLP, we also flatten, but then we concatenate, and then we actually pass through some dense layers. And the activation function that I used here is a ReLU, so it's a nonlinear one, which is the same one they used in the paper. After that, we concatenate the matrix factorization part and also the MLP part, and then we pass it through a sigmoid, and we have the outputs. So in this case, I didn't do the transfer learning that the paper proposes because I wasn't that invested in this demo, to be honest. But yeah, let's see. This was actually enough to have comparable results. So here is just compiling the model binary cross entropy for the loss, Atom for the optimizer, and then just here just some metrics that I can actually see here, right? So while the model was training, the layers. The data set, I went from the Pandas to a TensorFlow data set. So this is all I'm doing here. And then this is the training. So training took actually 1 minute and 20 seconds for 10 epochs. That's what I had set before. And then I generated the predictions, which took 3 seconds. And these are how the predictions look like on the long format, right? So for each user and item, what it is and what we have. And again, we're only taking the top K, right? That's the highest 5 in this case that we would be recommending for user 0. And if you put this in a wide format, this is how it would look like, right? So this is just kind of referring back to what we had originally. For metrics, I use the precision IK and recall IK. There's a lot of, like I mentioned earlier, evaluation is a big part of the recommender systems, one of the biggest hardships, right? So for this one, I just stuck to what's the precision at that top K items that we've recommended, right? So, and the recall as well. And these are the metrics that I've got. So again, you could go on and look at personalization, you know, are we just recommending the same items over and over? Are we recommending the most popular? There's a lot of things you can do to evaluate recommender systems, but for the purposes of this demo, I just stuck to precision and recall at K. And here did the same thing for the LightFM model. The LightFM model is just this, like this is fitting and predicting here. And took less than a second to do that. So it's way, way faster But in this case, we actually beat the LightFM model, not by a lot, but by a little bit. And when I did other runs of this, sometimes the LightFM model would beat the neural matrix factorization. So it would kind of depend. I mean, maybe you can fine tune this network more, or you can put more epochs or change the activation function. There are ways to try to beat it better, but I thought for the purposes of this demo, this was sufficient. And yeah, that's it. So just some closing remarks before we open for questions. So the neural matrix factorization, it does have a higher computational cost. Like I showed, it took 1.5 minutes to train and predict, whereas the LightFM model, it took less than a second. It has also slower implementation, right? Because you have to define the functions, you have to go through all that stuff. But it is an improvement in collaborative filtering. Since it has the matrix factorization bit, it should be at least as good as the matrix factorization, right? One thing that I could also do to try to beat the LightFM model was to do the transfer learning, right? So train the 2 bits separately and then just concatenate them in the end and fine tune, something that I didn't have time to do. Another thing that the neural matrix factorization allows us to do is play with the number of layers, activation functions, and do something more tailor-made for that data set, right? So we do have the flexibility as a plus. And we also could do some transfer learning, not only when we do collaborative filtering, the matrix factorization separately from the multi-layer perceptron bit, but we could also, if you're going towards a content-based hybrid with collaborative filtering, if you want to use NLP stuff, so like transformers, it would be easy to integrate that since everything would be on TensorFlow, right? So it would be easy to implement NLP stuff, easier to implement some NLP bits there and do some fine tuning as well as some temporal series. And those are some things that I'm sure, I think the paper also mentions as future work. And that's pretty much it. So yeah, if you guys have any questions, I'll be happy to answer them right now. Thank you for your time.
Thank you, Murilo. So far, no questions in the chat, but as you mentioned it, we'll post the recording on YouTube. So you can also add all the information, the links to the paper, these kind of things at the YouTube channel. The link will also be posted at our meetup channel. Okay, there was one in the chat, but it's just I got a question. Would you mind repeating the difference between those 2 branches of the network?
Here. Maybe I'll go here. It's more interesting. So this part here would be the multi-layer perceptron part. So maybe it's actually this bit here. It would be the same as this one, right? So we just have a matrix multiplication between these 2 matrices here. And this would be the collaborative filtering. So the matrix factorization bit, which is corresponding to the collaborative filtering method. So we just have a product between this vector and this vector to get the recommendation for this user and this movie, right? So it's really just that, and we do the machine learning to approximate these 2 matrices here. But on this part, it's actually just a neural network, right? So we have again, we have a vector here that we're also training. We're also learning this vector, and we're passing them through a neural network with nonlinear activation functions. So here's just a matrix multiplication. So element-wise product, right? If you have 2 vectors, it would be an element-wise product for that one user and one movie. And then here would actually be a neural network that is gonna output a value that is the likelihood of this user to like this item. Hopefully that's clear.
Yeah, so no non-linearities in the GMF layer, just a single variable decomposition approximation. There is also another interesting question, Murilo. So whether this approach suffer from the cold start problem and
Yes.
how you would tackle this in production.
So this is still collaborative filtering, right? So it still relies on the user item interactions. It still relies on this, right? So a cold start problem would be, let's say you have another user here that has no check marks. How can you approximate that, right? Like if you think of in the sense of actually factorizing this matrix, you still have that issue. Both of these methods rely on this interaction matrix. So you're gonna have the cold start problem, and the way to overcome it would be to just have a hybrid, right, between these two methods here, right? So if you have no input, you have no purchase history for a user, then you will fall back into a content base, which will take information from that user itself. And then once that there is a purchase, then you can go into another approach that has both of them. So.
Okay. Okay. Well, those are the questions in the chat. Thank you, Murilo, for your presentation. Thank you, everybody, for joining. We will post video recording of the session on YouTube. Post the link in the meetups page, and yeah, hopefully we will see you again at another Rootlabs at Lunch session. Thank you.
Thank you.